Alright, so in this video I'm going to be going through the OCR specification on electricity from module 4. So before I do so, I just want to outline a few things to make this as effective as possible. The first thing being, don't use this until you've actually gone through and studied electricity as part of A-level physics. This is designed as a revision tool, not a tool to actually learn things in the first place. And then also, I've put this in the description of the video. I put a link to the Word template you can see here. So what you should do is, at each section, you need to have a go at filling in each section before I go through it in the video. That way you'll identify the things that you know, the things that you don't know, and the things that you thought you knew but didn't have quite right, which are the important ones to find too. And the final thing in terms of this is not a task that you should do once. This is something you should do several times over a period of time as part of the revision process to help you gradually develop your knowledge. All right. So second thing to flag up is a resource I've created to help you practice your terminology, your units, all of those kind of things. And again, I'll put a link to it in the description. This is a tool called Memrise, which is a language learning tool, but it works really well for learning definitions. Okay. So let's get started with section 4.1.1 on charge. So these are the things that the specification says you should be able to do or know about charge. All right, so for the first section looking at charge, using the template I've given you, work your way through, see what you can currently fill in, and then we'll take a look through. All right, so I'm going to assume you've paused the video and gone through it. So let's start off with current, which is the rate of flow of charge or the number of charges per second. Either of those two is fine. And the way we model it mathematically is using the equation I is the change in charge or the charges that pass through over the time in which that happened. And then what we've got is current, we usually use the symbol I, as you can see there. Charge, we use the symbol Q. Current we measure in amps, which we usually just write an A for, and charge we measure in coulombs, which we write a C for. And for electricity, we use the elementary or the most fundamental charge as that of an electron, which is 1.6 times 10 to the minus 19. There are a few things that exist with a smaller or fraction of this charge, but these aren't things that affect electricity. So that's as fundamental as we all go. In terms of looking at the net charge of the lithium atom and ion, so atoms you should know are neutrally charged. A lithium 1+ ion means it has a fundamental charge of plus 1.6 times 10 to the minus 19. When we describe it as +1, what we're giving is called the relative charge, whereas what I've given is the net or the absolute charge. Okay, so when we're modeling charge in circuits, we use a law called Kirchhoff's first law, which states the sum of the currents entering a junction is equal to the sum of currents leaving that same junction. And this is essentially a law of conservation of charge, because what it really means is if a charge goes in, it has to come out. So it's just conservation of charge. So we can show an example of where we might use this. I've put a circuit together like this. If we're going to use Kirchhoff's law, we're going to need parallel sections so that we have some junctions in our circuit. And there are two junctions here, so we could apply it at this junction on the left-hand side, or as I'm going to, we could apply it at this junction on the right-hand side. So the unknown ammeter reading there would be 3 amps, because you just add together those two going in. Okay. So moving on to look at drift velocity, same process here, work your way through this short section and then we'll go through it. All right, so now you've had a go at this. Drift velocity, this is the average velocity that a charged particle attains due to an applied electric field. So in terms of circuitry, what that means, we've got a battery applying an electric field. Our charged particles are going to be our electrons, or sometimes we model it as being coulombs of charge. And the word average is in there because not all of them will go at exactly the same speed. Some will be faster, some will be slower, but there is a sort of an average that we call the drift velocity. So we can relate drift velocity to the current in a circuit using this equation here. And just to make sure you know what the symbols are, I is current, as we've seen before. N is the free electron density in the conductor. Maybe we're using a wire or something like that. And that's measured in electrons per meter cubed. A is the cross-sectional area of the conductor, and maybe we might need to measure that using a micrometer, something like that. E is the charge of an electron that we saw earlier, the 1.6 times 10 to the minus 19, and V is the drift velocity or the average velocity of the electrons. Okay, so we can use the idea of charge carrier density or electron density to explain what a conductor, insulator, and semiconductor are. So if something that's good at conducting, which we call a conductor, has a very high free electron density. How high? About 10 to the power of 29 electrons per meter cubed. So we have a lot of electrons there to carry the charge around our circuit. The opposite of that would be an insulator, which is a material with very, very low free electron density, because the structure of the material is not one that releases free electrons. And then sort of in between, we have materials called semiconductors, which have a high enough level of free electrons that they can conduct, but not as good as normal conductors. But the thing that makes semiconductors special is they respond to conditions changing. So if we change the temperature, the number of free electrons changes as well, which is useful. Okay. So moving on to 4.2, again, what I'd like you to do is work your way through the section, and then we'll stop and take a look through. All right, so let's go through our circuit symbols. Should be fairly straightforward. Our cell, power pack, a filament bulb, LDR, diode, switch, fairly straightforward. Then going down the second column, ammeter, fixed resistor, thermistor, and it doesn't matter if you do it the other way up, a variable resistor, an LED, so looks very like a diode just with the photons coming off, and then finally our voltmeter. This is not an exhaustive list, but these are the common ones that crop up as part of the course. So again, we're just going to put these to use, drawing some circuits with them. So first we've got a power source in series with a variable resistor, which is in series with a parallel section of an LDR and a fixed resistor. So that's what we can see there. So we can see the variable resistors in series with our cell, and then we see it splitting into a fixed resistor and an LDR. We're going to circuit with a cell, 3 light bulbs, 2 of which are in parallel, and switches to control the whole circuit and each of the bulbs individually. So that would look like this. So we've got 2 bulbs in parallel, we've got switches in each parallel loop to control them separately, and a switch next to the cell that's going to control the current through the whole circuit. All right, so moving on to look at EMF and potential difference. Again, these are the things that you should be able to do for this section. So work your way through it first of all. All right, so now you've worked your way through, let's take a look at each of these things. So potential difference first. This is the work done by a component, maybe a resistor, maybe a filament bulb, on each charge, and it has to have that in there, that it's on each charge, to decrease their energy, and we measure it in the unit of volts. Electromotive force is the kind of the opposite process, so it's still something doing work, but it's done to increase the energy, and it's measured for each charge or for each coulomb, so it's also measured in volts as well. And you might quite often see the word voltage in around books, maybe your teacher uses it, but they shouldn't really be. It's something that gets used interchangeably with EMF and potential difference, which is a problem because then you don't know which one you're talking about. So voltage, there is one specific case where we do use it, but most of the time we should avoid using the word voltage. So what we do is essentially look at the difference between potential difference and EMF, and the key is the direction of the energy transfer. So an EMF is increasing the energy of our charges or our coulombs. Potential differences are decreasing the energy, and that's the difference there. So now we're going to start thinking about how we can mathematically model these things. So we can relate EMF and potential difference to energy. So we said that EMF is the work done per unit charge. So if we multiply the EMF by the number of charges that have passed through, we would get the amount of total work we've done. And it's the same process with potential differences as well. We can just multiply by the number of charges that pass through. That gives us the total work done. So then what we can do is we can use this work done by the EMF to get an idea of the velocity we could get if we had an electron or an electric field. And we can do that by using conservation of energy. So using conservation of energy, if we do work on something, one of its forms of energy must change. And in a circuit, we don't think about gravitational potential energy, we don't think about elastic potential energy. So essentially what that's going to mean is the work we're doing with our electric field is going to increase the kinetic energy. So the charge of an electron is 1.6 times 10 to the minus 19, which we just write as E usually. The potential difference, or the EMF, whichever we want to do, and then we got that's going to be equal to the change in kinetic energy, which is going to be the final kinetic energy minus 0. Then what we can do is we can just rearrange that to figure out what the velocity is if we know the potential difference, the charge of an electron, and the mass of an electron. But if you plug these numbers in, you'll get fairly big values. These usually come out in the order of 10 to the 6. But drift velocity is usually about 10 to the minus 3. So explain why the drift velocity is considerably less. Well, this model hasn't factored in the work done by our resistances in our circuit, or the collisions of the electrons with atoms, or another way of expressing that is the interactions of atoms, the electrons with the atom's electric fields. They're both essentially trying to describe the same thing, but we've essentially ignored resistance in that model, and that's going to provide a force in the opposite direction. It's going to provide work to decrease the energy, so that's why we have a smaller acceleration and a smaller final velocity by a large factor. Okay, so moving on to now look at really what resistance is and how it works. Again, work your way through this section, then we'll take a look. Okay, so first of all, resistance, it's simply the ratio of potential difference to current, and we measure it in ohms, which is given the symbol omega. That's often expressed in equation form as R equals V over I. So this equation quite nicely explains Ohm's law, or models it anyway, because Ohm's law states that potential difference is directly proportional to current for a certain component if its resistance has remained fixed. So scenarios where Ohm's law might not work, if you allow the temperature to change for a component, that's going to stop Ohm's law working, which is why we need this condition of fixed resistance to allow us to use this law. Okay, so now some IV characteristics that you should know. First of all, a fixed resistor current should be directly proportional to potential difference, so that kind of makes sense. A filament bulb would not be an ohmic type conductor, so a filament bulb graph looks like this. So in the middle section it behaves very much like an ohmic conductor, but when it starts to get hot at the higher currents, its resistance starts to change, which is why the graph changes shape. Then looking at a thermistor, a device that responds to changes in the environment. So if the thermistor is hot, its resistance is low, but it still looks like an ohmic conductor. But if we change the temperature to when it's colder, we can see that essentially when it's colder, its resistance is increased. So for the same potential differences, we've got much smaller currents. So that's what our thermistor looks like. Then if we have a look at our diodes or LEDs, these two should be exactly the same. They have the same function in a circuit of only allowing current to flow in one direction. The only difference being an LED when current is flowing through it, will also emit some photons of light, and these happen to be more efficient than filament bulbs, which is why a lot of us are replacing our bulbs with LEDs. Okay, so describe an experiment to investigate the IV characteristics, so essentially those graphs of a component. So the setup we would need would look like this. We could do a similar setup with a variable power pack if that's what you've gone for, that's fine. But what we would do is first we'd turn on our circuit and we'd make adjustments to the variable resistor, and we want a nice big range of results, so we'd go between its minimum and maximum settings. But what we'd be after is 7 measurements of potential difference in current. Then what we can do is we can plot a graph of current versus potential difference, and if we want to know the resistance, it's the reciprocal of the gradient of that graph. But the thing we need to make sure is that we're not allowing temperature to change, so we should make sure we're turning it off between readings, so we're keeping temperature as controlled as possible. Okay, so now taking a look at an LDR. So we looked at one semiconductor earlier, the thermistor, and in a thermistor, as you increase the temperature, you decrease resistance. An LDR is very similar, so as the LDR absorbs more photons, more free electrons are released, which increases the charge carrier density of the LDR. And from the equation we saw earlier, if we have a higher charge carrier density, what we're going to end up with is a higher current, even if none of the other properties change. And if our current's higher, but our circuit, the potential difference is the same, what that must have meant is we've decreased the resistance of the LDR. So essentially, the function of an LDR is when light intensity on the LDR increases, the resistance decreases. Okay, so we're going to probe resistance a little bit more to understand some of the factors that affect it. So work your way through this section on resistivity, then we'll take a look. Okay, so first off, how do we calculate the resistivity, which is a unique value for every material? Well, it's calculated using this equation. So resistance times cross-sectional area divided by length. So we found out all the values for different materials experimentally, and to do that we need a very simple circuit. We just need a wire and an ohm meter, and we're also going to need a meter ruler to do some length measuring. What we're going to do first though would be to use a micrometer to measure the diameter of the wire, and we do it in a few different places, and from that we calculate an average cross-sectional area. Then what we do is we'd measure the resistance at different lengths of wire, so maybe 10 centimeters up to a meter, something like that. And we plot a graph of resistance versus length, and that would allow us to get resistivity when we multiply the gradient by the area. And the reason that works is if we rearrange that equation we had earlier to make R on its own, so on the y-axis, L was on our x-axis, so you can see the gradient is resistivity divided by area. So when we multiply it by the area, we get resistivity. Okay, so now we're going to look at some things we can do to actually change resistivity. So for most components, resistivity increases temperature, and the reason why is that as temperature increases, the atoms in a conductor vibrate with a larger amplitude and a larger energy. And that means each electron is involved with more collisions with atoms as it passes through, which decreases the current, which means the resistance is increasing. And in terms of explaining that to somebody, what you'd say is the resistivity of the material has increased. So a thermistor is kind of the opposite. So as temperature increases, you actually release more charge carriers in the material and increase the electron density. And then that means the current gets bigger, and that means the resistance is decreased. So a thermistor is a really special kind of device because most temperatures, their resistance increases temperature. A thermistor, it decreases. All right, so we've had a look at some of the circuitry properties and energy. Now let's look at power. So take a look through this very short section, then we'll go through it. Okay, so first thing, power dissipated by a component. We have three equations we can use to do that. P equals IV, P equals I squared R, or P equals V squared over R. All three should give us exactly the same answer if they've been used correctly. If we then want to work out the work done, well, if the power is constant, which basically means that if the current is constant, we can do that just by multiplying power by time, which is essentially the same as doing IV times time. And the reason we express it like that is because current and potential differences are things that we measure in an electric circuit. So one of the things you might be interested in if we're running a circuit, I don't know, maybe in a house or something like that, we might want to know how expensive a device is to use. So one of the pieces of information is that when the electricity company sends you a bill, they charge you a price of about 13 pence per kilowatt hour. So if we want to work out how much it is, we first need to look at the component's power. So if I don't know, if you're looking at a kettle, maybe it's a certain number of kilowatts. So we need the power in kilowatts. Then we measure the number of hours that we would run it for, maybe in a month. And then what we do is we multiply those three things together to get how expensive that device is to use, I don't know, per month or per year. All right, so now we're going to delve a little bit more deeply into circuits, looking at the different types that we can have. So again, work your way through this section. There's a few sections where I'd like you to come up with examples or questions to demonstrate the various laws. So do that now, then we'll take a look. Okay, so Kirchhoff's second law, the sum of the EMFs around a series loop is equal to the sum of the potential differences. And that's just an expression of conservation of energy. So what it really means is any work we do to increase the energy of the electrons is equal to the work we do to decrease them around our circuit. That's what keeps the kinetic energy and therefore the drift velocity constant. Okay, so design a question and show a work solution that requires you to use both the first and second laws in a circuit. So the question I came up with is I designed a circuit like this, and I want to find out what V1, V2, and A are. So first of all, to find V1, we would have to use Ohm's law because we know the current going through it and we know its resistance. So we know V1 is 15. So if we make the loop going through the battery and round through the bottom section of the graph, we make that the loop. If the total EMF spike is 35, we lose 15 across the 5 ohm, which means across the 20 ohm, we must lose 20 volts of energy per charge. And then if you want to use Kirchhoff's first law, we know that A plus 1 must be 3, because A and 1 will go into the junction, 3 will come out, so A must be 2 amps. So here's where we use Kirchhoff's second law, sum of the EMFs equals sum of the potential differences, and here is where we use Kirchhoff's first law. Okay, so now we're going to look at how we can combine big circuits together to make them simpler to model. So if you've got components in series, they're really easy. You can just add the resistances together to find the total resistance. Parallel is still fairly straightforward. We're just using a reciprocal rule to find the total resistance of components in parallel. But the key is going to be recognizing when two components are in series and when they're in parallel. So what we're going to do now is design a question and a work solution to it that uses these resistor combination rules. So I'm actually going to use the same circuit I had before, and I'm going to work out the current passing through the battery. So the first thing is to identify what we've got here. So we can see the 10 ohms and the 20 ohms are in parallel with each other because the charges must either go through the 10 or either go through the 20. So that's what I'm going to do first. I'm going to find the resistance of the parallel resistors, and then that parallel section is in series with the 5 ohm, so we can add those two together, giving us a total resistance of 35/3. Then we can essentially use Ohm's law to find out what the current is, and we can see it's exactly the same as we had before. It's 3 amps. So the mistake people often make in this is thinking that the 5 and the 10 ohm are in series, or the 5 and the 20 ohm are in series, but they are not, because all of the charges have to go through the 5 ohm, but only some of them have to go through the 10 or some of them through the 20. So we can't describe those as being in series. To be in series, all of the charges must go through both of them. So that we can also look at some laws to combine EMF sources as well. So if we have EMF sources in series, just like resistors, these will add together. So if they're in the same direction, then they're going to add together. But if they're in the opposite direction, they're going to cancel each other out because they're trying to force the electrons to go in opposite directions. Identical EMF sources in parallel act basically the same as one of the EMF sources by itself. And different EMF sources in parallel, you end up with an average of the two EMFs in the end. All right, so moving on to modeling in a little bit more detail, factoring in internal resistance. So again, work your way through this section, then we'll take a look. All right, so the way I explain internal resistance is it's a way of modeling the work done to decrease the energy in each charge that's happening inside our battery before it even gets out into the circuit. That's what we use internal resistance for. And this is the one time it might be appropriate to use the word voltage, but I'm going to call it terminal potential difference to avoid that anyway. So essentially, terminal PD is the remaining energy in each charge once they have left the terminals of the battery, so it's already been slightly decreased by the internal resistance. And we can essentially get expressions for it. So we usually use a little r for the internal resistance, big R for the external resistance, and then I is the current going through the battery. But in terms of relating that to terminal potential difference, it's expressed in this form. So using Kirchhoff's second law, we know the EMF must be equal to the terminal potential difference plus the potential difference across the internal resistance. Okay, so we can actually measure EMF and internal resistance for a given power source. So the circuit we'll need looks something like this. So we need a variable resistor, an ammeter, and a voltmeter measuring across the cell. So it's going to measure the terminal PD essentially. So we're going to keep the power source on a fixed setting, but we're going to change the external variable resistor. So we get 7 different sets of readings of terminal voltage or terminal potential difference and current. Then we, again, as before, between readings, we want our circuit turned off, so we're minimizing any temperature change. And what we're going to do is plot a graph of the terminal potential difference against the current, because that's going to make the y-intercept the EMF. And if we multiply the gradient by -1, that's going to give us the internal resistance. All right, so final section, potential dividers, another way of modeling series resistors. So first of all, work your way through this section, then we'll take a look. Okay, so a potential divider circuit will look something like this. It's any two components in series with each other, or we can have 3 or 4, it doesn't matter, as long as they are all in series. And as I was saying earlier, if they're in series, what that means is any charge that goes through one of the components must also have to go through the other ones. That's how we know they're in series. So an example we use potential dividers for is in sensor circuits. So this one, we want a potential divider with a thermistor, a fixed resistor, an ammeter, and a voltmeter across the fixed resistor. That's going to look like this. And then what we're going to do is describe how the ammeter and voltmeter readings change if the temperature of the thermistor increases. So as temperature increases, the resistance of the thermistor decreases. So as the EMF is fixed, that means the current in the circuit is going to increase. And if the current increases and the resistance of the fixed resistance is the same, Ohm's law tells us the voltmeter reading will increase. So what we're going to do is now have a look at the potential divider equation and actually show where it comes from. So the potential divider reading is what you can see at the end that says the potential difference across resistor 1 is equal to the EMF multiplied by resistor 1 over the total resistance. So this is an equation for a potential divider with two resistors in it. But it comes from Ohm's law. So the first thing we're going to do is get an expression for the current in terms of the EMF and total resistance. Then we're going to use Ohm's law for resistor 1, substitute in the current, and that gives us the equation. So what we can do is use that as a way of expressing what's going on in a sensor circuit. So this is a circuit that will increase the brightness of a bulb if the light intensity decreases. So the way it works is as light intensity decreases, the resistance of the LDR increases, and what that's going to do is increase the total resistance and therefore decrease the current in the circuit. And then if the current decreases, the potential difference across the fixed resistor decreases. So using Kirchhoff's second law, that must mean the potential difference across the light bulb would increase. But we could also explain this using the potential divider equation. So if the resistance of the light bulb LDR section increases, the potential divider equation tells us that the potential difference across that section would increase. So it's just another way of modeling series resistors. Okay, so that completes the electricity part of the specification for Module 4. I hope you found that useful to review and improve your circuitry knowledge, and hopefully you'll make use of my other videos doing the same thing for other topics.